This video continues our journey through two-dimensional NMR spectroscopy by looking at an example of COSY and HMBC. In this example problem, what we are asked to do is show all the expected HMBC and COSY correlations for the protons that are circled in these red boxes. We're going to indicate HMBC correlations with single-headed arrows, which means that we will start with the arrow on a particular proton, and we will show the arrowhead indicating the carbon that we observe a correlation to. For the COSY correlations, we will use double-headed arrows, meaning that the arrow has an arrowhead at both of the protons that are participating in that correlation. And this is a common way of going about illustrating on a chemical structure what correlations are observed as a way of visually representing to the reader of a journal article, for example, what correlations were observed and used to piece together the structure of an organic molecule. And so as we do this, what we need to keep in mind as our key information here is that the HMBC correlations, when we're thinking about what correlations we would predict there, those are going to show which protons are separated from which carbons by 2 to 4 bonds. So we will need to draw in arrows to represent the protons that are separated from carbons by 2 to 4 bonds. For the COSY correlations, correlation spectroscopy is that homonuclear correlation that indicates spin-coupled protons. And that is generally going to refer to geminal protons that are non-equivalent, as well as protons that are vicinal to one another will generally be spin-coupled as well. So let's take a look at what we would expect to see as our HMBC and COSY correlations in this example problem. I'm going to zoom in to the structure that we see here, which, by the way, is the structure of erythromycin. It's a common antibiotic. And looking at what we have here, I'm going to start with the methyl group, and I'm going to go ahead and fill in. This is a CH3. Now, when we think about the CH3, we expect that that methyl group, the 3 protons there, will show up as a single signal in the NMR spectrum because of the fact that it's connected through a single bond to the rest of the molecule, not a double bond. This is not part of a ring. So expect this to have free rotation around this carbon-carbon bond, and hence those 3 protons to be interchangeable, meaning that they are all equivalent to one another. They are indistinguishable in the eyes of the NMR spectrometer. So they are expected to have one chemical shift, and then we need to sort out what protons would we expect those methyl protons to show correlations to in the COSY experiment. So thinking about the COSY experiment, we expect to see that protons that are vicinal will show up in our COSY. And so a vicinal proton that we would have would be a proton right here, for example. And so in order to illustrate that, what we can do is using our arrow that has 2 heads to illustrate that there's a COSY correlation going on. We can connect those like so. And they are vicinal to one another. They are on adjacent carbon atoms, so we expect there to be a correlation appear there. As we come from the proton here, this would be our only vicinal position. In some cases, you may also see a correlation over to here, to the proton that we bonded right here, as a weaker COSY correlation. But the main thing that we observe is these correlations to vicinal positions. So I'm going to leave that like so. Thinking about at that same carbon atom, what would we expect to see in terms of the HMBC correlations, heteronuclear multiple bond correlations, from this proton to carbon atoms? And we're going to see correlations to carbon atoms that are separated by 2 to 4 bonds. So here is a 2-bond correlation would be to right here, because we have 1 bond connecting the carbon to the hydrogen and then another connecting carbon to carbon there. So that'd be a 2-bond correlation. That is the only 2-bond correlation. If we come over to here, this would represent a 3-bond correlation. because we go hydrogen to carbon, carbon to carbon, carbon to carbon. And continuing onward, we would also expect to see a correlation over to here. That would be another example of a 3-bond correlation. And as a weaker correlation, we do often see 4-bond correlations, which would take us over to here and possibly over to here as well as our 4-bond correlations. Those 4-bond correlations that I'm going to highlight in yellow here and also going over to here are typically much weaker correlations than the 2 and 3-bond correlations. And in fact, sometimes the 4-bond correlations don't even show up at all. So don't be surprised if you're piecing together the structure of a molecule and you don't necessarily see those 4-bond correlations that I have highlighted in yellow there. But this would be a comprehensive set of the expected HMBC correlations shown in blue with single arrows showing starting at the proton, ending with the arrowhead on the carbon. That would be our HMBCs. And then the COSY correlation that is expected is this red arrow that has 2 heads connecting the 2 protons that we would expect to observe a COSY correlation for in the NMR spectrum. So similarly, let's come down to here. And I will zoom in just a little bit there. And at this position, we would expect to have 1 proton. I can sketch that in explicitly. So there's our 1 proton. And thinking about the HMBC and COSY correlations, we'll start with the COSY correlations. So at this position, looking for the protons that are vicinal, there would be a proton here that is vicinal. Also over here, there would be a vicinal proton as well. And so we would expect to see correlations to both of those. So I'm going to draw the double-headed arrow here in red to illustrate that correlation. Another double-headed arrow coming over to here. And I'll actually go this way just to make things a little clearer. So we come over to here. And these would represent our correlations to the vicinal protons. So we're looking at the adjacent carbon atom and what protons are directly bonded there. Generally, if we're looking at this proton and we see a heteroatom, there will not be coupling through to the next atom there. So if you look and you see that there is an oxygen going this direction, don't expect any coupling to continue on past that oxygen. So if there were an OH group here, for example, there would not be coupling generally between that and the proton that we see here. And likewise, if we come on down, we're getting too far away to get coupling down to here. So the extent of the expected COSY correlations are what I've highlighted here in red. Then looking at HMBC correlations, so heteronuclear multiple bond correlations, looking at, when we look at this proton, what carbon atoms are 2 to 4 bonds away. So we'd expect a 2-bond correlation to here, because that is 2 bonds away, 1 and 2. We would also expect another 2-bond correlation over to this carbon right here, because that is also 1 bond, 2 bonds away. And then we can continue with a 3-bond correlation over to here, a 3-bond correlation to here, and don't forget you can go in any direction, so a 3-bond correlation to here, and a 3-bond correlation between that proton in blue and the methyl group here, because that again would be 3 bonds away. So 1 bond to get from hydrogen to carbon, 2nd bond is carbon-carbon, 3rd bond carbon-carbon there. So that would represent the extent of our 3-bond correlations. And again, much like with the COSY experiment, we generally don't see correlations that span through this heteroatom here, be it an oxygen or a nitrogen or whatever else there. So we wouldn't necessarily expect to see a correlation over to here, generally speaking. We could also potentially see 4-bond correlations. So if we continue over this way, we would find a 4-bond correlation over to here. That bond correlation, much like looking at the earlier correlations, the 4-bond correlation is often very weak or non-existent, so that's why I'm highlighting that one in yellow. And then coming in the other direction, coming this way, we would reach this oxygen atom here, so there won't be a 4-bond correlation there because there's no carbon to correlate to. And so the complete set of HMBC correlations I show here in blue, all spanning from that proton that's circled in red over to all of the carbon atoms that are 2 to 4 bonds away, and there are several there. And that's why HMBC spectra can become quite complicated once we start to think about the multitude of 2 to 4 bond correlations. But that multitude of signals can be very helpful in piecing together the structures of organic molecules when you combine that information with things like the COSY correlations that we see here shown in red, representing which protons are separated as being vicinal to one another. Now, in the second part of this example, we are asked to take this structure, which is a penicillin derivative, and we're asked to do the same thing. What I would recommend you do here is hit the pause button and see whether you can get the right answer to this on your own, thinking about what we just did in the earlier example. We are going to start by tracing out the expected COSY correlations, which I'm going to show in red with my double-headed arrow. So I'm going to sketch in, for clarity here, my proton. And I'm going to show, also just to keep track of things, the protons that are vicinal to here. And in this case, we actually only have one vicinal proton, because if we look at the proton here, we look at the adjacent carbon atoms, there'd be an adjacent carbon atom here, and that has one proton, so that's vicinal. We come over to here, there's no hydrogens directly bonded here, so no possibility of correlation. We come up to here, and there's a heteroatom, so that's going to not generally enable correlations past that. So in this case, the proton that we have in red on the left in that box is going to have an expected COSY correlation to the proton that I've drawn the double-headed arrow to. And we don't really see any other expected COSY correlations for this. On the other hand, for the HMBC correlations, if we take a look at our proton of interest here in blue, and we look for carbons that are 2 to 4 bonds away. So starting with the carbons that are 2 bonds away, to be systematic here, here's a carbon that's 2 bonds away, so I'm drawing an arrow to it. Here is a carbon that is 2 bonds away, so I'm drawing an arrow to it. Do not draw an arrow to the carbon that's directly connected, so don't draw this arrow that I just showed here. That would not be correct because that is a heteronuclear single quantum correlation, not multiple. And we want to show the multiple ones here. So we should go to here, which is 2 bonds, and here, which is 2 bonds as well. And then thinking about 3-bond correlations, because HMBC can go out to up to 4 bonds. We find if we go another step here, we run into a nitrogen. If we go another step this way, we run into a nitrogen. If we go another step this way, we run into a sulfur. And typically those heteroatoms are going to prevent longer range observation of correlations. And so as a result, for this particular proton, we actually have 2 HMBC correlations that we would expect, because going further out, you could think of as being blocked by the presence of these heteroatoms. So with that, we conclude looking at this example problem of specifying what correlations we would expect to see within a molecule. And a common way of representing that schematically is to draw the structure of the molecule and then use this arrow notation where single arrowheads indicate HMBC correlations between a proton and a particular carbon, and the double arrows indicate which protons have COSY correlations to which other protons, to provide us a schematic or a visual of how we piece together the structure of an organic molecule.